Diana. All right, guys, here we go. So the date today is the 7th. The topic today are rate laws and reaction orders. Shoot, is this going to work? I don't know. Is this stupid? No, we're going to be okay. All right. So, guys, you sort of see me fumbling here a little bit. So what we're going to do today is we're going to take the next step in this idea of reaction rates. But guys, what you're going to find out is what we're about to get into is the entire reason we study reaction rates. And so what I'm going to do is I'm going to totally, you're not even going to know the difference, but in my brain, I'm about to explode. Guys, this is probably stupid. Let's see how it goes. But I'm going to totally rearrange the way that I teach this material. Literally, we're going to start by doing what I've always done last. Again, I was groggy this morning as I was waking up, and I was like, I wonder if that would work. And then I started to convince myself that it would work. And so we're going to try it. I really think this is going to be okay. But if it's a disaster, you're going to have to bear with me and we'll figure it out together. So guys, this is then the big idea. What is the big idea of chapter 14? And what I want to do is I want to explain to you the big idea for chapter 14. But in order to do that, there are some things that you need to learn along the way. So let me explain to you now how we're going to do this. So guys, we're going to start by talking about the big idea for chapter 14. But then guys, after we're done with that, we're going to come to these ideas of rate laws and reaction orders. So once we understand the big idea, what you're going to find is that rate laws and reaction orders are the steps, the concepts, the foundation that gets us to the big idea. So the thing that I'm going to do differently with you today is normally what I've done with other years is I've taught this stuff, and then at the very end of the day, I've said, oh, by the way, guys, this is all headed somewhere, and let me introduce you to what that is. Today, what I'm going to do is I'm going to introduce you to the big idea first, and then we're going to step back and talk about rate laws, talk about reaction orders, understanding that this is going somewhere bigger, but we're not going to get to that something bigger until Tuesday. Kind of get the idea? Okay. So guys, what is then the big idea that this is all headed towards? And guys, I would encourage you to write this down. This is the big idea. The big idea for chapter 14 are what are called reaction mechanisms. So guys, let me explain to you reaction mechanisms in a nutshell. So reaction mechanisms go like this. I would encourage you to write this down with me. C3H8 plus O2 yield, and we're not even going to balance it, CO2 and H2O. Let's not even balance it. That'll be fine. So guys, what kind of reaction is this? Say it again. It's a combustion reaction. We have C3H8, which you may or may not know is butane. Isn't it? Propane. Sorry, it's propane, butane, C4H10, the one that's in our lighters that we're using in lab in a minute. So guys, this is propane. It reacts with oxygen and it makes carbon dioxide in water. But guys, this is going to seem initially kind of stupid and elementary, but then you're going to find out that it's kind of an interesting question. So guys, when we write reactions like this, we give the components of a reaction names. What do we call the stuff on the left? The reactants. What do we call the stuff on the right? The products. And so guys, if you've ever thought about it, when we write balanced equations, all that we are simply representing is what are the things that go in, the reactants, and what are the things that come out, the products. Can we all agree on that idea? Guys, here's the thing that we never talk about. How? How do the reactants turn into products? And guys, we have never talked about this before. We have never talked about what are the things that are going on behind the scenes that happen when reactants turn into products. So guys, I like to think about it like this. When you look at a balanced equation, it's kind of looking like at a birth announcement and an obituary. You know where that starts, and you know where it ends up. But guys, imagine if your life was only defined by your birth announcement and your obituary. What are we missing? Well, we're missing all the richness of what happened in your life between when you were born and when you were no longer with us. And guys, the same thing is going on when we look at balanced equations. We've got the birth announcement. We know what things look like when they get started. And we know what things look like when they finally stop, when the reactants turn into products. But guys, what we don't know is how. How does this happen? How do reactants turn into, what is going on as these reactants turn into products? Because guys, it's not this simple. This doesn't just run into this and magically turn into carbon dioxide and water. Do you see the idea? Guys, so the question that we're going to be asking over the next few days is, how does this happen? What happens when reactants turn into products? Guys, the answer to that question is what we call a reaction mechanism. A reaction mechanism is the series of steps that take place when reactants turn into products. Does that make sense? Guys, fundamentally, that's the idea. Reaction mechanisms are the series of steps that take place when reactants turn into products. And guys, that is the big idea for chapter 14. The big idea in all of this stuff for reaction rates is identifying mechanisms. How do reactants turn into products? Now guys, with that said, let me put your concerns to rest. You will never be asked to predict a mechanism. They would never give you this combustion reaction and say, hey, figure out how propane and oxygen turn into carbon dioxide and water. You'll never be asked to do that. What you will be asked to do is something like this. Propane and oxygen turn into carbon dioxide and water. Here is one possible way that could take place. Is this actually possible? Do you see the difference? Guys, you're not going to be asked to suggest mechanisms. You are going to be asked to verify mechanisms. And guys, this is where this is headed. So the big idea for chapter 14 is mechanisms, but you're not going to have to be able to predict. Well, you're not going to be able to make them up. You're only going to be asked to verify mechanisms given the ones that they give you. Is that okay? Okay, so guys, please don't write any of this down, but what I want to do is I want to sort of set the stage for you by laying out some ideas that we're going to be coming back to in the coming days about mechanisms. But guys, trust me, don't write these down. Just let them sort of rattle around in your brain, because this is all of this that's about to come up is going to be your notes for next class, so don't write it down now. So guys, imagine that we have this. Hi, thank you. Imagine that we have a reaction where simply A and B turn into C. So the question is, how does that happen? How do A and B turn into C? Well, guys, it turns out that actually by studying this reaction, the way that it happens is this. A is actually a molecule and A breaks apart. Don't write any of this down. When that happens, A breaks into what we're going to call A sub 1 and A sub 2. Then what happens, and guys, again, this is all hypothetical, what then happens is A1 crashes into B. And when A1 crashes into B, that forms A1B, and then A1B crashes into A2, and that turns into C. Guys, this is what mechanisms are like. When we write the balanced equation, all that we see is the before and after picture. This is the mechanism. This is actually the stuff that is going on behind the scenes that are actually the things that are taking place step by step as the reaction happens. And guys, these things are what are termed reaction mechanisms, the actual steps that go into these. Now guys, when we get into this idea of reaction mechanisms, the steps that make up a reaction mechanism are called elementary steps. Again, we'll talk more later, but these are what are called elementary steps. And guys, when we talk about elementary steps, these are the single steps that add up to the mechanism for the overall reaction. And when we talk about elementary steps, we describe them by what is called their molecularity. Those are the number of things that act as reactants. So guys, for example, this has got one reactant, so that would be what we call unimolecular. This has got two reactants, so that would be bimolecular, and this has also got two reactants, so that would also be bimolecular. So guys, we're going to stop right there. Just again, this is where we're headed on Tuesday, but I think you're going to find that this is helpful right now as sort of an introduction to what we're doing. But again, guys, none of this should make sense to you. What I wanted to do was introduce this to you now so that when we get into this on Tuesday, you have a sense of where this is all headed. So why are we studying rate? Why are we studying rate laws? Why are we doing the stuff we're doing? And the answer is we're trying to figure out reaction mechanisms. Mechanisms are the behind-the-scenes steps that actually are how the reaction happens. These things are what we call elementary steps, and we describe them by the number of reactants that are a part of them. So guys, do you have any questions that you need to get cleared up just because you're feeling like if I don't get this question answered, I'm going to be muddled moving forward? Understanding not rich understandings, but at least a general idea of what we're doing as we move forward. Okay.
I remember that in one moment, I don't know if it was in
Yeah. Yeah.
I remember that in one concentration, you put like reactants and then plus heat, and then
Good for you. Good question. And so the answer, let me see if I can rephrase your question. So is heat included in the mechanism? Is that okay? Is that sort of where, and the answer is no. So when we write mechanisms, what you're going to see is that it's only the things, the particles, the atoms and molecules that show up in the mechanisms. But that doesn't mean that heat's not important, because we remember that concentration and temperature are things that affect reaction rates, right? So when we talk about concentration, we're talking about the concentration of these things, the things that make up the mechanism. And that's actually the connection where all this is headed, is concentration is actually the concentration of the things that function as reactants in the mechanism. But also temperature changes the rate of a reaction, but it doesn't do it by changing the concentration of the things that are actually in the elementary steps of the mechanism. And as a result, the temperature heat doesn't show up in the elementary steps. Is that okay? Guys, other things just generically that you want to talk about? You guys okay? Okay, so let's pause for a second. Is it helpful for you to understand the big idea right now? Or are you feeling like right now, oh snap, I don't understand this, and as a result, I'm not ready to move forward? I guess what I'm asking you, has this done more damage than good? Because I've never done this before. Is it nice to have the big picture? Or would you rather have just stumbled into this blind? Big picture is good. Big picture is good. And just be honest, guys, I'm always learning, right? I pray the day never comes where I feel like I've got teaching figured out. So I really would love your feedback. Yeah. Okay. Yeah, if I had come and said, hey guys, this is the big idea, here it is, your response is, oh shoot, big idea, I better know it. But you do also understand that you do need to know it. It's just this really isn't all going to come together until Tuesday. Tuesday? Tuesday. Okay. So really, I haven't just blown your minds and we're okay. Go ahead, Maddie. See, keep going, sorry. Right. Mm-hmm. Right. Right, and I actually you have no idea the things that run through my head. Well, all good teachers, they've actually done studies on the inner monologue that's going on inside the head of a teacher as they're teaching, and it's fascinating. Like, good teachers are typically 3 to 4 minutes ahead of the class in terms of what's going on. And so I was actually thinking about mentioning, hey guys, this should be familiar relative to your chapter summaries, but then I realized I would probably alienate half the class because they don't remember doing them. And so I figured I should, but yes, if you did if the chapter summaries were meaningful to you, maybe this was starting to help you put some pieces together. So guys, any other feedback for me? I'm now curious to see how this goes, because if the rest of this goes well, I'm going to leave this switch permanently in my notes. So I'm still monitoring and adjusting, but let's see how this goes. Okay, so guys, this then puts a question before us. If we know that this is important, and if we know that this is coming on Tuesday, the question then becomes, how do we do this? How do we figure out mechanisms? And the answer is we don't. You will never be asked to predict a mechanism. The better question that we need to ask is, how do we know if mechanisms are possible or plausible? Again, they'll give you a mechanism. They will give you this, and they will ask you, could this be an explanation for how this actually takes place? So the question that we're going to pursue over the next couple days is, how do we know if it's possible? How do we know that this mechanism could work? And guys, this then leads us to what we're doing today. This leads us to what we call rate laws. So guys, not yet, but in a minute, you're going to want to start scratching things down. But what I want to do is I want to take you back to where we ended last time. So guys, in class last time, we looked at data that looked like this. So up until now, what we've done is we have looked at data that gives us time and concentration. And then guys, remember in class last time, we did some calculations that allowed us to figure out rate. We agreed that rate was change in concentration divided by change in time. And so we have time data, we have concentration data, and from that we can then figure out the rate of the reaction at any given time. Now guys, with this in mind, what were the interesting things that we learned about reaction rates last time? What's happening to this rate? Is it getting faster or slower? Why is it getting slower? Go ahead. Go. Of what? The reactant. So guys, we agreed on this interesting idea that reactions are always slowing down because they're consuming themselves. The concentration of the reactant is always going down. As a result, the collisions are less frequent. As a result, the reactions are slowing down. So guys, reactions are always decelerating because they're literally consuming themselves. Are we comfortable with that idea? Is that okay? Okay. So guys, this then is where we're going to move forward and where we're going to get into where we're headed next. So guys, the idea then becomes this. As we move forward, here's what we're going to do. And there's nothing here for you to write down, but this is going to be important. So guys, as we move forward, what we're going to do is we are now going to take a look at the factors that affect reaction rates and how we represent these effects mathematically. So how is concentration and rate connected? We already know they're slowing down. We know the concentration goes down. We know that the rate goes down. But guys, we're now going to talk about how to represent those relationships mathematically. To do that, let's consider another reaction. So guys, just allow yourself to sort of settle into this a little bit. So NH4, what's that? Not ammonia. ammonium, NO2 negative, what's that? Not nitrate, it's nitrite. And then that produces our good friend nitrogen gas and his little buddy water. So guys, we've got a reaction here where ammonium ion and nitrite ion is reacting to form nitrogen gas and water. Here's the data. So guys, what I'd like you to do is I'd like you to make sense of this data. Now guys, here's the problem. You look at this data, and to your eye, it looks amazingly like the data that I showed you on the previous slide. The colors are the same. It's in columns. Guys, there are all sorts of visual clues that your brain is tuning into and saying, oh, this is familiar. And you guys understand that, right? It's called schema theory. We learn by attaching new things to old things. It's called schema theory. And so guys, without knowing it, your brain is actually attaching this new thing to the old thing. The problem is this new thing is not like the old thing. What I want you to do is figure out, how is this data different from the data that I showed you on the previous slide? Don't talk about it yet. How is this data different? Once we identify the differences, we're going to talk about what we're going to do with this. But ask yourself the question, how is this data different? Now explain it to the person next to you. What do you see? How is the data different? Oh, did the light burn out? Yeah, shoot. I bought a new one. Guys, I'm going to pull us together in just a moment. You guys are brilliant. I love eavesdropping on your conversations. So, guys, to get the conversation started, I love the conversations about faster and faster and all these different things. But I heard, I think, Josh, but there was one observation that screamed, and I think it was Josh that said it, that is the fundamental difference between the data that we've been working with up until now and this. Josh, what's the difference? There's no time. Did you notice that? See, guys, this is the deception. Your brain up until now has been trained that as your eye scans down the columns, time is moving forward. This data has absolutely nothing to do with time. So as you see the reactions speeding up and slowing down, when you see the reactions speeding up as you go down, up until now that should have been problematic for you. Because previously you thought that as you go down, time moves on, and we agreed that reactions slow down. But guys, because this is not time-related data, all of a sudden we need to understand what's going on with these rates. So guys, let's talk. If this data does not represent a reaction progressing through time, what does it represent? Go ahead, Isaac. Very, very, very well said. Guys, we're going to use a name for what Isaac said. We're going to talk about these as trials. This says experiment number, but guys, you're going to find that the way to talk, especially on the AP test, experiment number is a lot of letters. Just call them trials. But guys, Isaac is exactly on it. But if you're not where Isaac is, then let's talk about this together. So here's how this goes. So guys, this is trial number 1 of the reaction. And Isaac, I love that you took the time to not just say concentration, but you said initial concentration. And that's critical. So guys, this is the way this goes. You know I love to draw beakers. So guys, imagine that you've got 2 beakers. And in the beaker on the left, you've got an ammonium solution. And in the beaker on the right, you've got a nitrite solution. And in this first trial, this is 0.01 molar and this is 0.2 molar. And what you do then is you dump them together, measure the rate, and throw it down the drain. You don't let this reaction happen over time. This is the observed initial rate. So you've got this, you dump them together, measure the rate, throw it down the drain, you're done. And then you start over. And then you do trial number 2. And this is now 0.02 molar. This is still 0.2 molar. Dump it together, measure the rate, throw it down the drain. Do you see the difference? This is not longitudinal data over time. This is initial rate data. And so the rates are changing, not because time is going on. The rates are changing because the initial concentrations are changing. Do you understand the difference? Okay. Guys, if you understand the difference, this brings up an amazing amount of new questions. So now, guys, let's talk. Let's think and then we'll talk. With your new understanding of what this data actually represents, what are the trends? What are the patterns? What in this data represents good science? And what can we take away from it? What are the trends? What are the patterns? Where's the good science? And what can we take away from it? Think about it for a second and then we'll talk. Trends and patterns, good science, and what can we take away? So guys, you've had a second to think. Now grab the person next to you and talk to them about it. Guys, I'm going to pull this together in just a moment. See, that's why we all need laser pointers. You know what, though? I had a dream once where my laser pointer actually hurt, and I got to use it as a student intervention tool. And seriously, the joy that brought me was probably wrong. But I was like, Santiago, knock it off. Bzz, and oh my gosh, it was so fun. That was a tough year. Good night. All right. Hey, so guys, what I loosely remember the questions that I suggest we talk about. But I don't know, I think I suggested it as the second question. Regardless, I'd like to talk about it first. The good science. So, guys, you understand that what we're trying to do is we're trying to connect concentration with rate. But in order to do that, when we're doing good science, guys, did you notice this and this? This and this, when we do science, when we do experimentation, this and this has a name. In an experiment, what do we call the thing that we don't change? Not the constant, the control. And so guys, here's the deal. In this data, we have controls. Why do we need controls? Well, guys, let me give you a looser example. Imagine if we were farmers and we cared to know what we could do to make plants grow bigger. Well, if we wanted to figure out what to do to make plants grow bigger, imagine if we went and we took some of these plants and put them in pots, and then we watered some of them, but didn't water others of them, but then we also put some in the sun, and then we also put some in the shade. Do you see the problem? If we then went back and measured how these plants grow, we wouldn't be able to attribute that to watering or sunlight because we were simultaneously changing both. So what we need is we need a control. So for example, we would water all the plants equally and we would change the amount of sunlight they receive. Then we would put all the plants in the same sunlight and then we would change the amount of water. The only way for us to be able to verify cause and effect relationships is by narrowing the number of things that we're changing. So we're only changing one thing and then looking at the effect of that change. Does that make sense? That's what scientists do. So guys, now let's do this. Let's take a look at trials 1 through 4. So if we take a look at trials 1 through 4, which one's our control? The nitrite. So if nitrite is our control, let's then, guys, take a look at the relationship between concentration and reaction rate. So guys, notice what we've done here. Between trials 1 and 2, what have we done to the concentration? Doubled it. What happened to the rate? It doubled. So guys, what about this? Between trials 2 and 3, what did we do to the concentration? Doubled it. What happened to the rate? Really close to doubled it. We're going to call that double it. Now guys, what about this? What about between trials 1 and 4? What did we do to the concentration? Quadrupled it. What happened to the rate? It quadrupled. And guys, we find out that these relationships continue throughout all 4 sets of data. So guys, the idea is this. When nitrite is controlled, any change that we make to the concentration of NH4 has a proportional change to the reaction rate. Let's say it again. With nitrite controlled, any change that we make to the concentration of NH4 has a proportional change to the rate of the reaction. Does that make sense? Are some of you right now in the back of your minds going, duh, if you double the concentration, the reaction's going to go twice as fast? Guys, if you're thinking duh in the back of your mind, very seldom is this the case. Guys, with most reactions, this relationship is not proportional. What you're going to see is you're going to see reactions where you double the concentration and the reaction rate quadruples. And you're going to see other reactions where you double the concentration and the reaction rate octuples. Some of you are starting to see the numerical relationship there. Guys, some of you are there are other reactions that we're going to see where you double the concentration and the reaction doesn't change at all. The rate doesn't change at all. And there are even reactions where you're going to double the concentration and the reaction slows down. So guys, understand On the surface, this looks like, duh, double the concentration, double the rate. But guys, understand it's not that simple. Sometimes you double the concentration and the rate quadruples, octuples, slows down, all sorts of crazy stuff can happen. Here's the question. Why? Why is it not that simple? Ready for the answer? Reaction mechanisms. Guys, the idea is this. The relationship between concentration change and rate change is fundamentally dependent on the mechanism. And mechanisms get complicated. Therefore, these relationships get complicated. Now I'm really glad I explained mechanisms to you first, because I couldn't have said that out loud had I not done that first. But guys, that's the idea. The relationship between concentration change and rate change, guys, this relationship is complicated because mechanisms are complicated. And that's where we're headed with this. Do you get the idea? Okay, but for now, guys, let's just say this. Double this, double that, so on and so forth. So, guys, now what if we look at the next set? Oh, wow. How did I do that? That was awesome. Shoot. Oh, good. Okay. All right. So, guys, what about the other set of data? Looking at 5 through 8, what's our control? Ammonium. And guys, you need to be able to talk about it this way. NH4 is our control. So if NH4 is our control, what are we changing the concentration of? Nitrite. So let's look. What's happening to concentration there? Doubles. What happens to the rate? Doubles. What about, I don't know. Here, what's the change? Triples. And what happens to the rate? It triples. And guys, there we also have a proportional relationship. Again, now hopefully you're not in the back of your mind saying duh, because we understand that these proportional relationships are often not what's going to happen, but for now we've got two proportional relationships. Does that make sense? Okay, now you're going to start taking notes. So guys, here then is how this goes. This is what we have now established. We're now going to write rate laws. So guys, scratch that in your notes. We are now finally ready to write what are called rate laws. So guys, don't write this down, but here is what this is based upon. We have now, again, you're not writing it down, but guys, we have now established that increasing the concentration of either one of the reactants while controlling the other one has a proportional change on the rate of the reaction. But guys, we can represent this mathematically. Write this down. Guys, this is how we say that mathematically. Let me zoom into it. Write it perfect. Earlier we said increasing the concentration of either one of those reactants, ammonium or nitrite, affects a proportional change in the rate of the reaction. Guys, this is that sentence in equation form. So, guys, what you've just written as you wrote that down is what is called a rate law. The term rate law describes that equation. So when they have you write the rate laws for reactions, that is the rate law for the reaction. So guys, let's dig into this idea of rate laws. Let's break it down, and then we'll learn some stuff from this. So guys, first of all, as I said, this is what is termed a rate law. And guys, when we write rate laws are simply a representation of the relationship between concentration, reactant concentration, and the rate for a chemical reaction. So here we have concentration, here we have rate. Sorry, backwards. Woo! Here we have rate, here we have concentration. But guys, what didn't we circle? K. K? Sorry. Come on. You thought his jokes were funny. Give me something. No, they weren't. Actually, they were. No, you're right. You're right. I stand corrected. Guys, let's talk about K. K is what is called the rate constant. Please write it lowercase, because in chapter 15 you're going to see big K, which is the equilibrium constant, which is products divided by reactants. You learned that last year. Don't get them mucked up. This is little k. So guys, little k is the rate constant. So here's what we're going to do. We are going to use the data from the previous table to figure out the value for k. What you're going to find out, guys, is that we can then use the, don't write this down, but we can use this information to then figure out the rate at any given set of concentrations. But right now, we are going to figure out the value for k. So I'm going to have to participate in this one. So remember how last time in class we broke into calculation groups? So you guys are going to do trial 1, trial 2, trial 3, trial 4, trial 5, trial 6. I'll do 7 and we'll just leave 8 out. So guys, again, 1 and 2, 3 and 4, 5 and 6, and then I'll do 7. So please, in your notes, calculate the value for k. So you guys are doing 1, you guys are doing 2, you're doing 3, 4, 5, and 6. Yes. Calculate the value for k. The rate constant. Holy buckets, y'all, really? So let me get you started. Rate is equal to k times NH4 plus times NO2 minus, how do we solve for k? Plug in rate, plug in the molarities, solve for k? Yeah, of course. Why does that keep happening? There's your numbers. Okay? Okay. Now you're solving for k. So guys, as you're doing this, let me just tell you right now, if there's a rate problem on the AP test, this question that you're now answering will be on the AP test. And it's one of the worst performing questions on every AP test. More than half of AP students get this question wrong when it's on the test. I'll show you why. I know that's not very encouraging in the meantime, but... So guys, did you all get your data? I'm going to zoom out. I'm doing trial 7, right? Okay, guys, compare with the people around you that are working with the same data. Yeah, I still might calculate. Thanks. Okay, guys, whether you're done or not, we need to be finished with this. So let's get together. Let me do the math quickly. So guys, 2 2 significant digits, we need, to the correct number of significant digits, we need 3. So K to 3 significant digits, 3. So I believe I got 2.67 times 10 to the negative 4th. What did you guys get?
I got 2.7 times 10 to the negative.
Perfect. What did you guys get? 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 What did you? Yeah. So guys, here's the idea. This is a rate constant. It is a constant. So it does not matter what concentrations you start with. It's a constant. And guys, if you then know the value for this constant, you could then start with any other set of concentration values that you want and then figure out the rate. Why does that work? Because it's a constant. But guys, that doesn't mean it doesn't change. You ready? What factors change the value of K? Temperature, surface area, and catalyst, huh? See where that just went? Guys, what are the 4 things that change the rate of a reaction? Concentration. That's right here. What else changes the rate of reactions? Surface area, temperature, and catalyst. Guys, those 3 things change the value of K. So when we say that the K value is constant, that means we're not changing temperature, surface area, or adding a catalyst. Get the idea? Okay, now let's have this conversation. You guys all got this, right? It's wrong. Guys, this is not the answer. We are all wrong. Here's why. Units. Guys, if you don't put units on your rate constants, they will give you 0 credit. The question is why? And the answer is this. The units change. So let's do this. How do we figure out the units for the rate constant? Well, guys, we need to put units on these numbers. Do this with me. Rate is given in molarity per second. And then our concentrations are given in molarities. So now, guys, we've got to do some math. So the way that this math works is molarity cancels with molarity, and molarity is now gone on the left and in one place on the right. Now, to solve for K, what we fundamentally do is take this number right here and divide it by 0.2 and then divide it by 0.0606 molar. And guys, when we do that, here's what we end up with. We end up with seconds in the denominator, and we end up with molarity in the denominator. Do you see that we're dividing by molarity so it comes over? So typically the way that we write that is not like this. We write it inverse seconds, inverse molarity. It does not matter what order. But guys, those are the units. This is getting even better. Guys, these are the units for K. Inverse seconds, inverse molarity. But guys, now you're going, wait, why is that such a big deal, and why do the AP authors get all hung up on it? You ready? Here's the deal. Guys, imagine that this reaction had another reactant. Imagine, I'm just going to make something up. Imagine that don't write any of that. Imagine that reactant was bromide. And imagine that we had some bromide in this reaction, and that then had a concentration that affected the rate of the reaction. Well, now, guys, what we're going to end up with is some number right here, which also has a molarity. And now, when we cancel our molarities, those cancel out, but now we've got 2 molarities left. which is molarity squared. And if we've got molarity squared, when we divide, we've now got 2 molarities down here, which means that's a -2. So if we add another reactant, this would then be inverse seconds and inverse squared molarity. Guys, that's why the units for K change. The units for K change depending upon how many different reactants we've got. Do you get the idea? But now, guys, why do we care about that? You ready for the answer? It tells us the molecularity of the reaction. Remember we said unimolecular, bimolecular, termolecular? The units for K tell us the molecularity of the reaction, which again, I couldn't have said to you earlier, but I can now because we did that first. So guys, fundamentally the idea is this. We care about the units for K, and it's not always the same. You've got to spend the time to track the units through the problem to figure out the units for K. Okay? Okay? I did it again. You know it's a good joke when you use it twice in the same day and it still keeps its meaning. You guys are tough. Tough. It wouldn't help. Are you guys good? All right. So, guys, with all of this said, what I want to do is I want to focus in on this idea of reaction order this idea of rate laws one more time, and we got to talk about something called reaction order, because this goes in your notes. So now that we understand rate laws, we now need to talk about an idea called reaction orders. So, when we talk about reaction orders, guys, what I want to give you now is I want to give you the generic form for a rate law. So stop. The generic form for a rate law. Guys, what do rate laws look like? They look like that, right? That's a rate law. So what is the generic form for a rate law? Well, guys, the answer is this. I would encourage you to write that down as well. Rate is equal to K. But I'm going to let you write down the right side of this equation without me reading it to you, because there should be something that you pause at when you write it down. And then the ... just means it goes on for however many reactants we've got. Guys, what caused you to pause? The exponents. What's that? The what? Yeah, the exponents. So, is that what you said? No, you guys don't get to be stupid like me. That's a one-way street. Bad humor can only flow in this direction. That's not even funny at all. And some of you are now confused because you think that's a second M for M&Ms. I know, because you stutter when you speak. You slur your... Okay, so guys, I can't even say this out loud. We need to talk about those letters. Don't write this down because it's simple, but you need to hear it. Guys, those letters have names. I just got to say, those letters, M and N, have names. They are what are called, don't write this down, they are what are called the reaction orders. Now, guys, remember when we did the previous rate law, we said concentration doubles, rate doubles, concentration doubles, rate doubles. And I told you it's often not that simple. Well, guys, these exponents account for that complexity. These exponents are what are called reaction orders. And they represent, again, you're not writing this down because this is simple. Guys, they represent the relationship between concentration change and rate change. So it goes like this. If you have a zero order reactant, and if you double the concentration of that, the rate doesn't change. That means that whatever this reactant is, it doesn't have an effect on rate. How can that be? It's all about the mechanism. But then, guys, if you have a first order reactant, and if you double the concentration of that reactant, you double the rate. That was what we saw. Double NH4, double the rate. Double NO2, double the rate, right? Okay. But guys, it doesn't stop there. You can have what are called second order reactants. And here's how it goes. You double the concentration, you double the concentration, you quadruple the rate. But it doesn't stop there. You can also have third order reactants. And guys, if you have a third order reactant, you double the concentration, you octuple the rate. So guys, let's do this. What's the relationship 2 and unchanged, which is 0, 2 and 2, 2 and 4, 2 and 8? What is that mathematical relationship that describes that? See, we've got 2 right here, but then we go 0, 2, 4, 8. What's that relationship? It's an exponent. 2 to the 0 is 0, or is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. So guys, these numbers right here, 0, 1, 2, and 3, those are the exponents. But we're not going to call them, sorry, I don't even want to talk. All right, you get the idea? So guys, this then brings us to the idea of what are called overall reaction orders. Don't write this down. But overall reaction orders are the sum of the exponents. So guys, in the previous reaction, and let me scratch it down quickly, here's the way we talk about this. That was pretty fast. Guys, how do we talk about this? And here's what we say. What is the exponent right here if there's nothing there? It's understood to be a 1. And this is also understood to be a 1. We don't write the 1s. But here's how we say this. This reaction is first order in NH4, it is first order in NO2, and it is second order overall. Just add up the exponents. Does that now make sense? Okay. So guys, with all of this said, here we go. We're going to write the rate law for this, and then we're done. This is the last thing we're going to do today. So guys, here's another set of rate data. I've obviously shot a picture out of a book and then just cropped it and threw it up on the wall. But guys, we are going to write the rate law for this reaction. So in order to write a rate law, we need to figure out the relationship between concentration changes and rate changes. And we need to do that for both reactants, A and B. So guys, let me give you a second. Don't write anything down yet. I want to structure this for you, but I want you to have the time to think through the logic. So how does changing the concentration of A change the rate? How does changing the concentration of B change the rate? And guys, I don't ask that hypothetically. Think about it for both A and B, and then you'll talk together, and then we'll talk as a group. Do you have some ideas? Share them with your neighbor. Do you need a lifesaver? So, guys, I'm going to pull this together, and we're going to do this twice. The first time we're going to do it conceptually. The second time we do it, we're going to do it well. So, guys, please do not let yourself become satisfied with doing this conceptually. Because if you do it conceptually, but you don't do it well, you will get no credit for this on the AP test. It matters how you talk about this. So, guys, let me lead the conceptual conversation. What do we know about A between trials 1 and 2? It is the control. What are we doing to the concentration of B? We are doubling the concentration of B. What does that do to the rate? Nothing. What does that make the reaction order for B? It is a zero order reactant. Does that logic make sense? Okay. Now, what are we doing between trials 1 and 3 to B? It is now our control. What are we doing to the concentration of A? Doubling it. What are we doing to the rate? Quadrupling it. So what does that make the reaction order for A? And the idea, if you're not seeing it, is this. We doubled, let me do it this way. We doubled the concentration. We quadrupled the rate. So 2 to what power is 4? 2. And guys, as a result, that means that A is a second order reactant. Does that make sense? Okay, now guys, this will lead us, and I'm going to encourage you to write this down with me, but I'm going to ask that you skip about 6 lines in your notes. Skip down some space, and guys, we are now ready to write the rate law for this reaction. So rate is equal to always a K. But now, guys, look at what we established. A is our control, B doubles, rate doesn't change. What is the reaction order of B? 0. So it doesn't go in the rate law. Any number to the 0 power is 1, so it's just a 1. It doesn't belong there. But then, guys, this. Double the concentration, quadruple the rate. So relative to A, what is our reaction order for A? We already established it. Second order. That is the rate law for this reaction. It is 0 order in B. It is second order in A and second order overall. And if you write this on the test, you will get no credit. Because you have no support for why this is true. So guys, let me show you how to bring this up to speed. So guys, what we've got to do is we've got to put in words the reasoning that led us to this. So guys, when you do this, here is what you've got to do. You have got to identify the trial numbers that you're looking at. You have got to identify the concentration. Sorry, not true. You have got to identify your control. Then you've got to identify your concentration change. Then you've got to identify your rate change. Then you've got to identify the order. So let's do that again. Trials you're looking at, the thing that's controlled, the change in concentration, the change in rate, and then finally the reaction order. So guys, this is the way this goes. I would strongly encourage you to write this down with me, basically word for word. Referring to, is referring 1 R or 2? 2, right? RR? Referring to trials 1 and 2. You've got to tell your reader which trials you're looking at. Referring to trials 1 and 2. When concentration of A is controlled and concentration B is doubled, rate doesn't change, making B a zero order reactant. Guys, drink in the logic behind what we just wrote down. We identified the trials. We identified the control. We identified the change. We identified the effect of that change. And then we identified, based on that, the order of that reactant. You see how that goes? You okay? And then when we write the rate law, there's no B in the rate law because it's zero order. Good? Okay. So guys, based on that, you write the next sentence. You now need to come up with a sentence that identifies the reaction order for A. You have a model in front of you. Craft your own sentence. How you guys doing? So do this. Share your sentence with the person next to you. And person next to you, please give them valuable feedback on what they wrote. Ethan, I think you should just FaceTime Parker. No. And even if he did, he wouldn't know what you're doing. Christian, I'm going to come be your partner. What'd you say? Okay. Okay. Yep. Yep. Boom. Boom. So guys, your goal in this entire process is to be like Christian. That's your goal. All right, so guys, I'm going to pull us together. We now have a couple seconds left. Allow me, if you would, to simply parrot what I just heard Christian say. He said this, referring to trials 1 and 3, where the concentration of B is controlled, the concentration of A is doubled. Doubling the concentration of A quadruples the rate of the reaction, making A a second-order reactant. Yeah? So, guys, there's your homework. Oh, yeah, it actually is this short. No, it really isn't. It's really just kind of this. So guys, let's take a break. If you need to polish your pre-labs for the lab that we're doing, I would encourage you to grab those, realizing I'm going to check them off as soon as we get back after break. Take a break. See you in a minute.